Greetings, Earth enthusiasts. If you ever wondered about the incredible perspectives our planet has to offer from high above, you're in the right place. I am Dr. Clive Coetzee, and I'm thrilled to be your guide on this captivating journey into the world of remote sensing. Welcome. And please remember to like, subscribe to, and share this video. Thank you.
In this video tutorial, we will continue working with our built-up urbanization, human settlement layers or data sets as per the previous couple of video tutorials. In this one, we will specifically focus on the version 3 open buildings data set as can be used within the Earth Engine. And we're also going to focus on bring into our analysis digital surface model and a digital terrain model to determine the height, or to see if we can calculate or estimate the height of the buildings. Because remember, within the data set itself, you have the size of the structures, the urban structures. Okay. I basically indicated, I think, in the previous one that it may be interesting to see whether we can generate the height of the building so that we work in a 3D environment rather than just a 2D environment. Okay, so continuing where we left off, remember we used the open buildings data set using or from its website itself, where we generated a region of interest in QGIS, and we brought that into our Colab notebook, and we generated the CSV Excel spreadsheet where we have the long and the lat, or the centroids of each structure. We've got a confidence level of each structure, we've got a size of each structure, and then the polygon details of each structure. And we said, okay, we can do that via the Open Buildings website, but if we want to continue working within the Earth Engine, we can then either import that data set within Earth Engine, within the assets, and that's something that we may do in a later video tutorial. We can bring that, as I said, within the assets, because in the assets, if you go to assets and new, it's got an option to bring in a CSV file. Okay, so we can potentially bring that CSV file in from the Open Buildings website itself. And the beauty of that is that we could have done all sorts of analysis with, or calculations or whatever within the CSV file itself, and then bring that in. And we then don't have to do that in Earth Engine per se. We just basically call up those features or characteristics. So that's something we can do. Or we can simply just use these project links. And these projects links are projects that other individuals have done, and we can find them within the Awesome GE Community Catalog website. So for example, the latest version 3 Open Buildings is available, and if you scroll down, there's obviously the source of it, where you can give citation and acknowledge the data source, and it will give you, if you look at here, the sample codes, very similar to the catalog within the Earth Engine. So this is an awesome site as well for some interesting data sets and codes and scripts and all these things. So have a look at it. It's worthwhile spending a little bit of time of it, but remember, as always, make sure that you acknowledge the data source, make your references very clear. So we used this particular project as our initial Open Buildings source, and we indicated that it certainly misses a number of urban structures, especially the latter urban structures. So this is probably fairly oldish data set that is not very complete. And so then we went to this particular data source, And we then change it from version 1 initially to version 3. And this is just filtering, the percentages. Remember, we said it's going to be green, orange, and red. Okay, so and then we've the latest version of this is, as I said, produced by Vida. And that is even newer than the version 3, or more updated than the version 3. And that is the code for that specific data set. There it is. And you do the same. You clip it for your specific region of interest using the filter bounds, or you can use the map clip tool or the clip.table tool. That's up to you. And then we display it, and I created export as well. Now, just to compare these three sources, remember they fundamentally use the same underlying source, which is the Open Buildings one, which is a digitization of all these structures. But they have different time horizons or time spans. So I've created a calculation or estimate of the number of buildings or structures contained within each data set. So it's just simply print what I'm going to print. I'm going to print this image. Remember, there's the image, which is this feature collection here. And then remember that it's not an image collection, it's a feature collection. So it's the multiple locations, not multiple images. Okay, so there's no need to generate a median or whatever, because it's not different images, it's just different locations. So that's why it's a feature collection. We clip it, and we just basically, and that's also where the problem comes in trying to export it, because you can't export a feature collection per se directly from Earth Engine. But nonetheless, and that's why I prefer to work with it in each website itself. Nonetheless, so let's see what the calculations are. How many features are there within this particular data set? Remember, this is the initial data set that we looked at. And if you say print the region of interest, meaning that specific feature location, that's a number, 21,597, that one there. So that's the number of features within this feature collection, meaning the number of structures. Okay. And then we said, okay, let's, remember we updated this to version 3, which is, I think, somewhere in 2023. And we calculate the size of that feature collection. And the size of that feature collection is 47,505. So more than double the initial one. So basically a doubling from version 1 to version 3 of structures. But it could be argued that most of that increase is just the small ones. But let me not speculate. And then we've used this particular data source, this Vida data source, in terms of its use of Open Buildings. And we generated that. Okay, so let's ignore the, in fact, we can cancel the export. There we said, let's calculate it. I've given that feature collection a variable name called Roy SA for whatever reason. Again, that's up to you. Remember, just to increase it there or to align it there in terms of what you're going to add to the layer. And then we print it, and you see it's 50,033. So you can see the significant increase from a difference in the number of urban structures contained in each feature collection. And you can see it's quite significant. So my suggestion is use the latter version. And again, you can most probably do the same in terms of confidence levels, etc., etc. Okay, but nonetheless, let's have a look and quickly see how that specific looks. Let's just take that way, that way, that way. Okay, so let's compare the three. And there they are visually. Let's go back to our satellite image. Let's go back to that apartment set next to the hospital. Where it is, there we go. There it is. Okay, so we said this is a fairly recent development here. So apartment buildings, it's hospitals like an old age home. There's apartment buildings, and this is the hospital itself. And we said that our initial image or feature collection, buildings. Remember that's the initial one. It only contains, what's it, 21,000? It only contains, 21,000. Let me just do that. Structures, 21,000 structures. That excludes, you can see, all these later developments and stuff. And so if we then include the version 3, activate the version 3, you'll see it also, it actually covers those ones. And then if we add the latest one that we've generated, you can see it also covers those ones. Interesting, as I said, it doesn't cover them as individual buildings. Let's have a look and see. It covers them as one big building because they're one solid structure. They're not loose standing structures. Okay, so you can see they definitely cover this one. Let's go to that beachside development and see if there's any difference between this. Okay, so there's one there. Let's go and have a look and see. There's our initial version 1. You can see it covers maybe a couple of them. You can see there, just one here. Okay, there's a couple there, but a couple there. Nothing to the latter development, nothing there. So let's go to the version 3. There we go. It covers, as I said, much more, a number more, almost double more. And then if we have the last one, let's just wait for that one to finish. Okay, so the yellow is the medium confidence levels. And we have the latest version. It's still basically the same. There's no difference between. Now there's a couple of, you can see there, some differences between the two versions. You can see that, that's for sure. But in general it covers, it misses the same buildings basically. But it's much more complete than the version 1 layer. So, but as I said, what we'll do is we'll bring in the spreadsheet and then compare those two. But what I want to show, okay, so within those data sets that we displayed, let's go for the latest one. It will give you the size of the buildings. Okay, so the data set will contain the size of the buildings, meaning the length and the width. But that, as I said, gives you a nice two-dimensional picture. What we want to see is where we can create a or to generate a three-dimensional picture of these urban structures. Now, to do that, we need to work with a digital terrain model and a digital surface model. Now, digital terrain model basically just indicates the earth, the surface of the air, excluding everything that's on the surface, meaning whether there's trees or poles or buildings or whatever the case might be. It basically just looks at the surface of the earth as if it is a bare piece of earth. There's nothing on the surface, just a bare piece of earth. That's your digital terrain model. Now, your digital surface model indicates not just the bare surface, but what is on the surface of the air. So it will capture buildings and trees and all these sort of things. But remember, we have to subtract it because the terrain model by itself will have a height. Okay, because the terrain model indicates the height above sea level, and the digital surface model will also indicate the height above sea level. So you have to subtract these two to get an indication of the height of the item or the feature on the surface of the Earth's surface. So, for example, if you're at location X, and location X, let's say there's a house there or a tree there, then it would have it will have meters above sea level. So, depending again how far or how high you're from the sea. So, let's say I'm at location X. Okay, so let's quickly just look at this, for example. You see there's my sea level there. So obviously that would be very close to sea level. Okay, so these structures here would obviously have a very low digital terrain value, or not the structures per se, but the Earth's surface here. Whereas if you go inland, let's say to this position here, then that by definition will have higher digital terrain value than this value. So to equalize the two, to get the height of, let's say, something here and compare it to height with something there, we have to subtract from each one the digital terrain value, because that assumes the Earth is flat. It doesn't assume that this area by definition will be higher than this area simply because it's higher than sea level. So what we have to do is to say, okay, for any specific location, call it point X, we will have two height levels. We'll have a digital terrain level, which is simply just the height of that level from seaside or sea level. Okay, so that's just that level above sea level in meters. And then it will have a digital surface value, which will be if there's a structure or a feature on the surface of the Earth. So that will also be a height. If there's nothing, so it's just bare soil, the two numbers should theoretically be exactly the same. So for example, here, that's a bare piece of land. There's nothing on it, that piece of land there. There's nothing on there. There's no shrubs, no bushes, no vegetation, no buildings, no nothing. So theoretically, this site should have exactly the same digital terrain value than the digital surface value. Okay, but you can see there is a shrub there. So that value, and let's say this value here should have exactly the same digital terrain value, because it's roughly the same distance from the sea, height above sea level. However, because it's got a structure of a tree there, it should have different digital surface values. And therefore, to get what is the size of the tree or the height of the tree, we have to subtract the digital surface value from the digital terrain value. And that will give you theoretically the height of whatever you are looking at. Now, it's obviously not always that straightforward and it's simple, sadly, but let's see if we can make that work. Let's see if we can figure this one out. Okay, so if we go into our Earth Engine and we go to data sets and we go to search, we can say give us terrain model, terrain model. Okay, so it will terrain with the A. So there, terrain model. So there is a number of them. So let's go and have a look and see data sets tagged DM. Okay, so let's go data set tag DM, and you'll see there's a whole lot of them. A lot of them obviously is not relevant to IAM because I'm not in Australia, Northern Netherlands, etc., etc. But there are ones that are for the world. There's a digital elevation model. Okay, so there's a digital elevation model, and there's a digital surface model. You can see there's a digital surface model. So there is two models, and then you have to be careful which one you use. There's another digital elevation model. Let's have a look, and there's a digital terrain model. Okay, obviously these ones might not be relevant. It's up to you to go and have a read through it and see which ones are them. So there's a digital terrain model. Let's have a look and see what this one is. There's a global multi-resolution terrain elevation data model. This is for 2010. Yeah, I remember it's something that's most probably not going to change. It's a single image just for that period. Let's have a look. The data contains elevation data for the globe collected from various sources. Vision is available. Here is blah 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 blah. Critical within a landscape maintaining in minimum elevation or maximum value and break line that passes within a specific analysis window. Okay, so you can read with, and obviously there is the code. Let's have a look at that. The bands. That's the band value. It's elevation. It's in meters. There's a resolution. It's not too savvy. And there is the minimum, and that's the maximum. Obviously, that will be above sea level. Okay, so let's have a look and see if there's anything else, terms of use and citations, nothing there. Okay, so that's a digital terrain model, and you can obviously go in, further go in, do a bit of research on it to find out whether it is sufficient to use or not. So there's the one. Let's have a look and see where was our digital surface model. There's our digital surface model. Let's have a look there. Let's go and click on that one there. The Copernicus DM is a digital surface model which represents the surface of the air, including, remember this is important, including buildings, blah, 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 blah. Okay, so this would include it. And so therefore you can't just use it because obviously a small building very high above sea level will appear much bigger than a very big building close to with a very low sea level height. So therefore you have to obviously subtract height above sea level, and therefore the terrain model. Okay, and there it is. That is its script or code. Okay, so you basically just go, or you can just go to, so we can go there, elevation, we can type in elevation as well, model, see if we can get the same, Copernicus data sets, DM, and you're going to get to the same data sets. Okay, just remember, have a look for them, read for them, get an understanding of exactly what you're looking for. Digital surface model. Let's have a look. This one here, what was the other one? Was 239, I think was its resolution. This one is 30 meters. DM it is its band. Okay, so nonetheless, okay, so we copy them, and I'm going to use this particular data set. Let's have a look and see. Let's go to its landing page. We go to the search one. We paste it in there. We entered. And there it is. Let's have a look and see what this one is. Global 30 meter version 3, 26. This is a image collection. Obviously, we're going to go to the median of it. Get the middle one. Again, that's up to you. You see, here's the height above sea level, minus 433, height above sea level, sin 60, 11, converted. And we look at the description. It's based on, and it is latitude, etc., etc. There is its script. So that's the digital surface model that I'm going to, let's go back. Where is it now? Yeah. It is a digital surface model. Okay, so that's the one that I'm going to work with. That gives you your digital surface. And then I'm going to work with this one. Let's go there, go to data sets. Let's go and have a look at that one. And this is the terrain one. Okay, so that's the terrain one, terrain elevation model, and this is the digital surface model. Digital terrain model, and this is the digital surface model. Okay, so those are the two that I'm going to use. Let's see if they are compatible. I am concerned about the resolutions. This is 231, and this one is 30 meters, so it's not ideal. There's also differences in the date of these images, which is also not ideal. This is elevation 457. Let's have a look and see. For the plus minus the same 4787. And yeah, so the minimum and maximum are very, very similar height above. Okay, so let's stick with those two for now, and we're going to use them. And then obviously we're going to subtract the two. Okay, so I'm going to then, I've created a variable we called CHM, which is calculated a canopy height model. That's right. CHM canopy Okay, so that will be canopy height model. Sorry, I'm gonna have a Google search for it. There's quite a bit of literature and work around that. I'm just at this stage, I'm not following necessarily what has been done in prior research and what is suggested. We're just playing around with this for now. Okay, so then I'm taking the DSM model, which is obviously the one which will be a higher value, simply because it will already have the height of sea level, above sea level included in it. And then I'm subtracting the sea level, height above sea level. Okay, and that will give me my canopy height model, or my values. Okay, which theoretically should be the height of what is on the surface at that specific location. Theoretically, okay. So there is my digital surface model, and I'm using this specific data set. I am clipping it to my region of interest, okay? Because it's an image collection and there's multiple images, I'm going to use the median indicator or statistic to generate a single image. Again, you can use the sum, you can use the mean. That's up to you. Play around with it too to see what generates the best results. It may just be in this case that using the mean may be the better option, but let's play around with it. And then we have the color palette, and then we add it to our layers. And we do the same with our DTM. We clip it because it's a single image. I can't use this specific method of clipping because that relates to an image collection. This is a simple image, so I'm just going to clip it as a single image. So I use this particular method. And no need to do a medium or whatever because it's single collection image, single collection. I generate a color scheme for it and I add it to my layer. And then I create a color scheme for the difference, or my canopy height model, or the height. Create a color scheme for that, and I'm going to add it to my layer. Okay, so on top of all the build-up, urban settlement, urban footprint, urbanization layers, we're now also going to add these three layers, which is a digital terrain model layer, a digital surface model layer, and let's call it a canopy height model layer, which is simply the difference between the first two. Okay, so we've visualized all these other ones already, so I'm not going to go for that. Let's visualize our digital surface model, and there it is. Let's go out because it is better viewing it from quite a distance. It's not looking well. You can see the dark blue is obviously lower levels. Sorry, must be digital terrain model first. Must swap them around. So remember, the digital terrain model is image of the surface of the Earth as if it's flat. There's nothing on it. Okay, it's a flat piece of land, nothing on it. Okay, and there it is. But it's in gray. So that's not a very nice color scheme. So let's go to its little nut there. Let's click on that. Let's give it a color scheme. Again, are these numbers correct? We don't know the range. Let's stretch it and then apply. Okay, that looks a little bit better. And then let's give it a color scheme. So we're going to do, what shall we do? We want to go low levels is blue, and let's dark blue and light blue, and then we're going to go to basically to our reds. Let's go pink. Now let's go that color, and then let's go for red, and we're going to apply. Okay, so let's see. So that gives you, okay, so let's import it. Okay, so I'm going to import that colors pull it. I'm going to use that one. That's the image versus for the DTM. Okay, that looks a little bit better. So it indicates basically, remember this is mountainous areas here. If you look at it, it's a mountainous area. So mountain is higher above sea level. The more red, the more blue is the lower to sea level. You can see the rivers quite clearly being very low to sea level. You can see the coastal areas being very low on sea level, etc. So you can already see quite a bit of stuff on there. Okay, so let's go to the next one, which is our digital surface model. Let's play around with its details a little bit. Let's also go to a stretch function there, and let's see how that looks like. Okay, so that, let's see if we can give the same color scheme. So I'm going to subtract that one, and this one I think we said was something like that, and then we had a the last one, which is dark red, and this one I think we had a color somewhere closer to that. So let's do apply here. Theoretically the two should look fairly similar. Let's import that one as well. Okay, so the two should look very similar. Let's have a look and see. Yeah, they look fairly similar, except color schemes are a little bit different. Then we said we subtracted the two. Okay, so let's quickly have a look at that. So that's not a very nice color scheme, so let's quickly state that one as well. So let's make that one dark red. This one becomes like pinkish color, and this one is more like a brown color. Let's do that one. I'm gonna just copy this one. I want to make that previous one looks similar. Okay, so let's close it, and we're going to import that as well. What's the DSM that we made? There we go. So let's change that to that color scheme, and we apply it. So now the color scheme should be, that one I think was 2. Yeah, I think something like that. Okay. So I think the color schemes are plus minus the same now. So let's have a look and see. There's our digital terrain model. There's our digital surface model. Okay, digital terrain model, digital surface model, digital terrain model, digital surface model. And then obviously that's the difference between the two. Where blue obviously is going to be very little difference, and the more red it is, the higher the difference. Well, we'll have a look at it now. Okay, so we've created those ones, and obviously we have our buildings. Okay, so let's zoom into our trusted town. Let's just wait for the layers to load. Should load fairly quickly because it's not very big layers. Okay, and there's the last one there. Okay, so let's ignore the layers for now. I'm just gonna, okay, so let's go to a particular, okay, so let's look at, I know this is an apartment complex. Let's just take this out of there as well. You can see this is clearly an apartment complex. You can see that 3 stories apartment complex, which is basically very close to the sea. There's the sea, so it should have a low digital terrain value because it's fairly close to the sea. In fact, it's basically on the sea, so it should have a small digital terrain value. Sorry, there we go. It should have a small digital terrain value and a higher digital surface model, and the difference between the two theoretically should be the height of this building. Okay, so let's hold thumbs and see what happens. Okay, so how do I'm going to do this? I'm going to do my inspector, and I'm going to click on the building itself. So let's just any place on the top of the building. Let's just minimize the first ones. We're not interested in any of those ones. What we're interested in is the digital terrain model. So that's 4 meters above sea level. This building is 4 meters above sea level. The building itself, or the whole thing, is 9 meters. And then if I subtract the two from one another, I get my digital height, so that's 5 meters. So this is suggesting that this building is 5 meters in height. Okay, let's take it at face value. Let's see if that's going to work. Let's take this particular. We have to be careful because it's in pixel resolution, so you can't, just assume. Let's place it next door because it will capture still some of this data, even though we're at this site, simply because of the resolution. So you have to be a little bit more tricky. You can't simply just click on that. Let's click on that one there. You see it will give you the same digital terrain level 4 there. Digital surface model is indicating 5. Yeah. So it says that the height of this is 1 meter. Okay, that could be grass, could be a bit of shrubs, etc., etc. So, but you can see the difference. Okay. So on first glance, it looks okay. So this also looks like apartment buildings. This is houses. This is a road. There's a house there. Let's have a look and see. There it looks like a fairly big house there. Okay, let's click on this one here. Let's see what this one looks like. So digital surface model is 0, and digital. Okay, so this means it's 0 height. That's questionable. Don't disagree. Let's click on the road, see what that says. I said the alignment is not always perfect, so that means on this road the terrain is 6, so that seems to be standard. The terrain here is about 6 meters above sea level, and in this case the digital surface model indicates a height of 7, so meaning the road is 1 meter in height. I don't think that's true. Anyway, let's see if we can find another. Okay, so let's go to this intersection here. Click on that intersection. And there we go. Okay, so here it works that the terrain is 7 meters above sea level and the digital surface model is 7 meters. So in this case, it's 0, which makes absolute sense. Let's look at this building here. This is a normal shop, little shop there. Let's have a look. The terrain model, remember, is 6 there. So it indicates the terrain model is 7. Digital surface is 10. So it indicates the height of this building is 3 meters, which makes sense because it's a single story shop that. Let's click on these bushes now. You have to be fairly accurate on where you click. Again, it could be alignment. It's not always perfectly aligned. So it indicates the digital terrain there is 7. The digital surface model is 8. So it means these trees are about 1 meter. Okay. It's a bit small, but anyway. So it gives you the indication. As I said, you can basically generate. Let's have a look at say this building here. This is a 1-story warehouse type thing. Okay, so in this case, it's a -1. So there is a little bit of an issue here, is that the digital terrain indicates 9 and the surface model indicates 8. So that's not properly correct. Let's click in the middle of it. Okay, as again, so you'll see now there's some. You see here, we can see there. Digital is 8, 6, so that seems a bit more accurate. It's a 2. Okay, so let's click on that point there. And the problems here is simply because of the resolutions that don't align properly. So you have to be in fairly, so take it as a fairly broad location, not a specific location, because there's not perfect alignment between the resolutions. The resolutions, one is 30 and the other one is much higher. So you may have these anomalies. But I think in general, it does seem okay. Let's have a look at this building. Let's have a look at another place here. Let's have a piece of, okay, so that looks like a piece of bare soil. So let's click on that and see what it says. Yeah, you can see 6 and 6 and 0. So that makes sense. Let's say, where was that other piece of land here? Okay, so let's click on this. This looks like a bare piece of land here. Let's click on that. 23 and 30, so that's maybe simply a bit of a hole or something. Let's click on this one here. See what happens there. 28, 24. Okay, we can't really see what's on there, because remember, this is an image as is. Okay, this is the image in 2023 most probably, but remember that digital terrain was done in 2010. Okay, yeah, so there could have been something different there in 2010. And this is most probably same as with some of these buildings. I know, for example, this wasn't here in 2010. Definitely wasn't there in 2010. Maybe one part of it. So that's what I'm saying. You need to take these things with a pinch of salt, because the digital terrain model is 2010, and which shouldn't be too much of a problem. But the digital surface model is 2011. So these buildings were not there. So that's what I'm saying. Although the digital terrain most probably is not going to be an issue, the digital surface model is a bit of an issue. So we may have to look for a digital surface model that's a little bit more up to date than this one, just to have more accurate information. But I think you get the idea. I think you get the idea is that we can use these surface models, or these terrain models, or call it elevation models. We can use them to generate a height, a surface height, what we call it, canopy height, and that's why I call it a canopy height model. I think you get the idea that we can work with those sort of images to generate some indication of whether these buildings, or what's the height of these structures, these built-up structures. And we can obviously then include that within that CSV table, so that we don't just have the height of the size of these structures, but also have a height of these structures. So now all of a sudden you have a 3D image, and then in your GIS applications, in my case QGIS, we can display this in a 3D model, which is obviously visually much more appealing than just generating a 2D model. Okay, so we're going to continue working with this, but I think you're starting to get the idea, and hopefully you are excited with what we can potentially do, working with different data sets, combining these two data sets to get a third, call it attribute or feature. Okay, we're going to continue working with this and see what else we can do on this. But yeah, thanks for joining me for this particular video tutorial. And in general, thanks for joining me on this journey of remote sensing. Please remember to like and subscribe and share and all these fancy things. Welcome to communicate with me. I'll appreciate your feedback, comments, suggestions. Always most welcome. And I'll see you on the other side.